Hello everyone, I'm Paul and today we're solving problem 3372, maximize the number of target nodes after connecting trees 1. This is a medium problem and I think this is great if you want to practice graphs, so keep watching for the intuition, approach and efficient solution. We have two undirected trees and we know that whenever we read this we are talking about a graph, because let's say we have node A which connects to node B and to node C. We can go from A to B or from B to A, okay? That's undirected. We can go in both directions. We are also given an integer k which represents the maximum levels that we can traverse from the source. You will see what this means in a few minutes. Now we can connect one node in one tree with another node in the other tree. And we need to return an array answer where each answer is the maximum possible number of nodes that we can traverse without exceeding k from each source in the left tree, in the first tree. Let's see what this means with an example. Let's say we have these edges. Let's say this is edges 1 and this is edges 2. From this we can build two graphs. Now remember, we need to return an array of the size of the left tree, in this case f5, where each index in the array corresponds to the maximum amount of nodes that we can traverse from each node in the left graph. For example, let's say we start from 0 and k is 2. We can traverse this node, this one, this one, this one, this one. We can connect this with this and traverse this one, this one, this one, and this one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. So the result at index 0 will include a 9. Okay? And we need to repeat the same process for every other node in this left graph. Now you can solve this with DFS or with BFS. We are using BFS here because I think it's more intuitive. Remember that in BFS we are moving to adjacent nodes in circular ways. So from 0 we move to 1 and 2 and this will go like this, okay? And when we are implementing DFS, we are moving from branch to branch. So for example, we move first here, then here, then here, and so on. Now let's say that we are at this node once again, and from here we want to connect this with this tree. Now the question is, where should we connect this node exactly? Because we can connect the 0 with this 2, or maybe with this 0, or maybe with the 3. The question is, what is the best choice that we can take here? And we will have the same questions for every other node here. Let's say we are at 2. Here we have the same question. Where should we connect these two? Should we connect this here? Or should we connect this here? Now, to avoid repeated work, we can find the maximum amount of nodes that we can traverse in this tree with a value of k minus 1. And then we just add that value to whatever we get in this tree. So we will do a breadth first search in this tree first with a value of k minus 1. Remember, this is our limit. So for example, let's say we start from this source and the current level is 0. So up to this point we have one node. And from here we can move to every adjacent node, meaning 2, 3, and 1, and we can add this, this, and this to the result. So now the result is 4. And we are currently at level 1. because remember, this is level 0 and this whole thing is level 1. And given that our limit is k minus 1, meaning 1, we cannot traverse any more nodes, so the maximum value that we can get from this source is 4. So we know that from 0 we can get a 4. And we will repeat this same process with every other node in this tree. Now let's say this is the source and we are currently at level 0. So the result up to this point is 1 for this source, and from here we can move to every adjacent node, meaning this and this. So we add 2 to the result. This is now 3, and here we are at level 1, which is equal to k minus 1. So we end here, and this is the value for this source. Similarly, from here we will get a value of 1 plus 1, so this is 2. From here we will get 1 plus 1, which is also 2. From here we will get 1 plus 1 plus 1, this is 3. From here we will get 1, 2, 3, 4. From here we get 1 and 2. And from here we get 1 and 2. And with this information we can take any maximum value. So we can take this node or this node. Let's say we take this one, for example. This means that from here, for example, we will connect this with 0. We will also connect this with 0 when this is the source, and we will connect this with 0 when this is the source, and so on. And every time we are adding to the result for each of these nodes a value of 4. So for the final array, let's say we are at this source where the node is 0 and k is 2. So from here we move to every adjacent node. Up to this point we have a result of 3 for this source because of this node, and this node. And this is level 0, this is level 1, and this is level 2. K equals 2, so we can keep moving for one more level. So next we move to every adjacent node from these 2. We move here and here, and the current result for this source is 5. And remember, we are always connecting this node with the maximum result we got on the right side. So 5 plus 4 equals 9. So we put a 9 here. Because think about it, k is 2, and up to this point we are at the first level, and from here we can move one more level to every adjacent node. So we also add this node, this node, and this node. So in this side we have 4 nodes, and this is where this 4 comes from. Next we are here at level 0, and the result for this source is currently 1. And from here we move one level to every adjacent node. So this is level 1, and we also grab this node. So the result is now 2. And from here we move to every adjacent node. So we move here. This is level 2. So we add one node here. This is now 3. And remember that we need to connect this node with this one. So 3 plus 4 is 7. So we add a 7 to the final array. Now we are here, this is level 0, and from here we are moving to every adjacent node. This is level 1. So here we have 1, 2, 3 nodes. So the current result for this source is 3 plus 1, 4, and from here we move one more level, so this is level 2, we grab this and the current result is 5, and we need to add the right side, so 5 plus 4 is 9, so we add a 9 here. Next, this is the source, this is level 0, so the current result for this source is 1, and we move to every adjacent node, meaning we move here, so we add a 1 here, this is level 1, and from here we move to every adjacent node, we move here and here, so we add a 2 here, and remember we need to connect the source with the right graph, so 1 plus 1 plus 2 plus 4 is 8, so we add an 8 here. Next, the source here, this is level 0, the result for this source is 1. We move to every adjacent node, meaning we move here, this is level 1, so we add a 1 here, and from here we move to every adjacent node, meaning we move here and here, this is level 2, and 1 plus 1 plus 2 more nodes plus the nodes on the right side for this is equal to 8. So we add an 8 here, this is the end, and we return this. Time complexity for this will be big O of n squared plus m squared, because we are doing BFS from every source in the right graph, and we are doing the same in the left graph, and space complexity will be big O of n plus m, because we are building adjacency lists for every graph. In case you don't know how to build adjacency lists, you will see how in the next part. So now let's go with the code, and hopefully you will get the idea. First, we'll build adjacency lists for both graphs. This is very important for any graph problem, and an adjacency list is basically a map where each key is every node in the graph, and every key connects to an array which contains all the values the key connects with. Here we need to build two adjacency lists. So to make the code efficient, we'll create a function. We'll call this build adjacency list, and this will take some edges, and here we'll create a map. We'll call this adjacency. This will be a default dictionary with a default value of an empty array. We can do that like this. And now for every A and B values in edges, we add to adjacency at A, B, and we add in adjacency at B, A. And finally, we return the adjacency list. So, as you can see here, we have an undirected graph because we are connecting A with B and we are connecting B with A. Remember that if the graph is directed, you will have something like this, for example. And now we can create our two adjacency lists from edges 1 and edges 2. We'll say adjacency 1, adjacency 2 equals build adjacency from edges 1 and build adjacency from edges 2. Okay, Now n equals length of edges 1 and m equals the length of edges 2. And here we can build the breadth first search function. So BFS, this will take a start node, an adjacency list, and limit. And every time we are doing a BFS, we need to use EQ. We can implement this with a deck in Python. We use this to pop elements from the left, which is what EQ does. And here we need to put an array, and in here we'll start with a tuple, which will contain the start node, a level 0, and a parent of -1. We'll use a parent to prevent multiple countings, prevent cycles basically. So just to be clear, this is node level parent, count equals 0 initially, and while we have a queue, well, we have something in the queue, queue.pop left, this will give us 3 values: node, level, parent. Now we can add 1 to the count, and for every neighbor in adjacency lists at the current node, if the current level is smaller than the limit, than this limit, and the current neighbor is different from the parent, we add to the queue a tuple with the neighbor, level +1, and the current node. Okay, remember that we are doing this to prevent cycles. And now we can return the final count. Now we will get the maximum count for the graph in the right, for the second graph. So we will start with maximum 2 equals 0, and for every index in the range from 0 up to m+1, because m is included, we can get the maximum value like this: max2 equals max2 BFS, the current index. We are using the second adjacency list, so this is adj2, and we are using k -1 as the limit. Remember, this is very important. And one more thing, if k is 0, this should be 0. So here we can say if k is greater than 0, we run this loop. And now result is an array with 0 times m+1, and for every index in the range m+1, result at I equals breadth first search, I, the first adjacency list, adj1, k, remember here we have k -1, and here we have k, and here we need to add the maximum value in the second graph, mx2, and finally we return the result. So this is the entire code, and now we'll submit this and see if it works. And as you can see, this works and it's efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.